Waveguides between parallel planes. So we are deriving the field components by considering this figure. So in this figure there are two conducting planes of infinite extent in the y and z direction. So these planes are separated by a distance of a meter in x direction. The space between the planes is air or free space. Now to solve this, we have to consider the boundary conditions for perfectly conducting planes are Et equal to 0 and Hn equal to 0, where Et is the electric field intensity's tangential component and Hn is the normal component of the magnetic field intensity. Now we are using the Maxwell's equation. The Maxwell's equations in the dynamic field are used here. So first we are using del cross H equal to Js plus dou d by dou t, where Js equal to the conduction current density and dou by dou t is the displacement current density. Del cross H equal to sigma into E plus dou by dou t of epsilon into E, where Js equal to sigma into E, which is the conduction current density, and D is equal to epsilon into E, which is the electric flux density, and dou by dou t equal to j omega, which is the phasor form representation of dou by dou t. Here sigma equal to 0. So the equation becomes del cross H equal to j omega epsilon into E. Consider it as equation 1. Then del cross H equal to, we can write it as in the determinant form, that is Ax, Ay, Az, dou by dou x, dou by dou y, dou by dou z, and the vector components h, hx, hy, and hz. So we have to solve this. So del cross H equal to, we can solve it as Ax into dou by dou y of hz minus dou by dou z of hy. So this is the component of the unit vector Ax minus Ay into dou by dou x of hz minus dou by dou z of hx. Now plus Az into dou by dou x of hy minus dou by dou y of hx. So consider this equation as 2. So when we look into the equation 1 and 2, the left hand side are same, that is the del cross H are same. So we can equate it. So equating equation 1 equal to 2, the equation becomes j omega epsilon E equal to Ax into dou by dou y of hz minus dou by dou z of hy minus ay into dou by dou x of hz, dou by dou x of hz minus dou by dou z of hx plus az into dou by dou x of hy minus dou by dou y of hx. So the equation becomes like this. Vector E equal to Ex Ax cap plus Ey Ay cap plus Ez Az cap. Now we have j omega epsilon vector E equal to j omega epsilon E x Ax cap plus j omega epsilon Ey Ay cap plus j omega epsilon Ez Az cap. Ez cap. So the equation becomes j omega epsilon Ex Ax cap plus j omega epsilon ay cap plus j omega epsilon az cap equal to ax into dou hz by dou y minus dou hy by dou z minus ay into dou hz by dou x minus dou hx by dou z plus az into dou hy by dou x minus dou hx by dou y. Now comparing the coefficients, we get dou hz by dou y minus dou hy by dou z equal to j omega epsilon ex. Equation A. The next component is dou hz by dou x minus dou hx by dou z equal to j omega epsilon ey. Equation B. And the next component is dou hy by dou x minus dou hx by dou y equal to j omega epsilon ez. Equation C. So these are the three equations. Del cross E equal to minus dou B by dou T, Maxwell's first equation in dynamic field. And the magnetic flux density, that is B equal to mu H. And dou by dou T equal to j omega, the phasor form representation. The Maxwell's first equation in dynamic field was derived from the Faraday's law of electromagnetic induction. Now considering the equation del cross E equal to minus j omega mu H. Equation number 3. Now the curl of the vector. So del cross E can be also represented in the determinant form. That is determinant ax, ay, az, dou by dou x, then dou by dou y, dou by dou z, then the electric field components ex, ey, and ez. Now we have to solve this. For that, we have to find the determinant. That is equal to ax into dou by dou y ez minus dou by dou z into ey or minus ay of dou by dou x ez minus dou by dou z ex plus az into dou by dou x ey minus dou by dou y ex. That is equation number 4. We are repeating the process we did before. So that is minus j omega mu vector h equal to minus j omega mu. The vector h can be represented as hx ax cap plus hy ay cap plus hz az cap equal to minus j omega mu hx ax cap minus j omega mu hy ay cap minus j omega mu hz az cap. Equating the equation 3 equal to 4, that is minus j omega mu hx ax cap minus j omega mu hy ay cap minus j omega mu hz az cap equal to ax into dou by dou y of ez minus dou by dou z of ey. minus ay into dou by dou x of ez minus dou by dou z of ex plus az into dou by dou x ey minus dou by dou y ex. Now, comparing the coefficients, we will get the equation similar to the equations we got before. That is, comparing the coefficients, we will get dou Ez by dou y minus dou Ey by dou z equal to minus j omega mu hx equation D. The next component dou Ez by dou x minus dou by dou z of ex equal to minus j omega mu hy equation E. Similarly, dou Ey by dou x minus dou by dou y of ex equal to minus j omega mu hz equation F. These are the 6 equations we got A, B, C, D, E, F. Now, the wave equations will be del cross E equal to sigma mu dou E upon dou t plus epsilon mu dou square E upon dou t square. So, this is the electric field component of the wave equation, and we also know that sigma equal to 0. So, the equation becomes del square E equal to epsilon mu dou square E upon dou t square. So, dou by dou t equal to j omega, that is dou square by dou t square equal to j omega the whole square. We know j square equal to minus 1. So, which is equal to j square into omega square, that is equal to minus omega square. Now, the equation becomes del square E equal to minus omega square mu epsilon into E. And we can take it on the left side. The equation becomes del square E plus omega square mu epsilon E equal to 0. That is equation 5. And similarly, we can write the magnetic field component of the wave equation, that is del square H. That is, we know that the del square H is the magnetic field component equation of the wave equation, that is del square H equal to sigma mu dou H upon dou T plus epsilon mu dou square H upon dou T square. And here we know sigma equal to 0. Then the equation becomes del square H equal to minus omega mu epsilon H, which implies del square H plus omega square mu epsilon H, which is equal to 0. That is equation number 6. The wave equation for the perfectly conducting planes are del square equal to minus omega square mu epsilon E and del square H equal to minus omega square mu epsilon H. And now the wave is propagating in z direction, and it is represented by e raised to j omega t minus gamma z, where gamma is the propagation constant and alpha plus j beta, that is alpha is the attenuation constant and beta is the phase constant. Since the space between the planes is infinite in y direction, the derivative of all the y component will be 0 because y is a constant and y is constant or a uniform. So considering the field component hy which is varying in z direction, it is given by hy equal to hy naught into e to the power minus gamma z. Now differentiating with respect to z, the equation becomes dou hy upon dou z equal to hy naught into minus gamma e to the power minus gamma z, which is equal to minus gamma hy naught into e to the power minus gamma z. From this we can infer that hy naught e to the power minus gamma z is hy itself. So it is written as minus gamma hy. That is dou hy by dou z equal to minus gamma hy, which is equal to or which implies dou by dou z equal to minus gamma. Now on substituting dou by dou y equal to 0 and dou by dou z equal to minus gamma in equations a, b, c, d, e, f, we will get dou hz by dou y minus dou hy by dou z equal to j omega epsilon ex. Now we know that dou by dou y equal to 0. So this is 0 minus minus gamma hy equal to j omega epsilon ex, which implies gamma hy equal to j omega epsilon ex. And the next dou hz upon dou x, okay, it was my mistake, dou hz upon dou x minus dou hx by dou z equal to j omega epsilon ey, which implies dou hz upon dou x minus minus gamma hx, which is equal to j omega epsilon ey, which implies dou hz upon dou x plus gamma hx equal to j omega epsilon ey. The next equation dou hy upon dou x minus dou hx upon dou y equal to j omega epsilon ez, which implies dou hy upon dou x equal to j omega epsilon ey. Similarly, dou ez upon dou y minus dou ey upon dou z equal to minus j omega mu hx, which implies minus minus gamma ey equal to minus j omega mu hx, which implies gamma hy equal to minus j omega mu hx. Next, dou ex upon dou z minus dou ex upon dou z minus dou ez upon dou x equal to minus j omega mu hy, which implies minus minus gamma ex minus dou ez upon dou x equal to minus j omega mu hy, which implies gamma ex minus dou ez upon dou x equal to minus j omega mu Hy. And the next equation is dou Ey upon dou x minus dou Ex upon dou y equal to minus j omega mu Hz, which implies dou Ey by dou x equal to minus j omega mu Hz. Now, solving these equations, we will get Hx, Hy, Ex, Ey. These are the field components. Now, Hx equal to minus gamma by h square dou Hz upon dou x, and Hy equal to minus j omega epsilon upon h square dou Ez upon dou x, and Ex equal to minus gamma upon h square dou Ez upon dou x, and Ey equal to j omega mu upon h square dou Hz upon dou x. While examining these equations, Hx, Hy, Ex, Ey all depends on the Hz and Ez. Now, if Hz and Ez are 0, there would be no field components. So, it is necessary that Hz or Ez or both should be present. Then there will be field components. Otherwise, there would be no field components. And while examining these equations, the h square is common in all these, where h square equal to gamma square plus omega square mu epsilon, and the only positive field component is Ey. So when we study these equations in a by heart manner, we have to remind in a way that always the field component Ey will be positive, and the Hx, Hy, when considering these two equations, the Hx depends on the Hz and Hy will be Ez. When Hx and Ex are compared, the Hx depends on Hz and Ex depends on Ez. When the field components depends on the Z component, Hz or Ez, then the numerator will be minus gamma. When Hy and Ey are compared, Hy depends on Ez and Ey depends on Hz. The Y component of the magnetic field will depends on the Z component of the electric field, and also the Y component of the electric field will depend on the Z component of the magnetic field. The derivations of these equations will be in the next video, and I hope you liked it. Thank you for watching this video.